So welcome everybody to another stream today. Today we're going to be talking about Rust strings and everything that you've ever wanted to know about strings. This is going to be a little bit different than my previous stream. We're going to still code a bunch, but there's not going to be one kind of overarching example to work through. We're going to go through the docs quite a bit. We're going to talk about it. We're going to talk a little bit about theory and stuff like that. We're going to try some things out and look at some stuff and try and get familiar with how strings work inside of Rust, and chat, relying on you for any questions that you might have, anything that you want to explore. And as always, it would be really great if people could give their feedback on what you like, what you don't like about the stream, things that you want to see in the future. I got a couple of ideas lined up. Some people have been asking about async await, which is a huge topic that I am still trying to figure out exactly where to begin or what things to talk about. And FFI is something that I'm working on a day-to-day basis. So how do you talk to other languages using Rust? So we'll probably give that a go in the future. But if you have any ideas, just let me know. But with that being said, I think we'll get started and we'll start talking a little bit about strings in Rust. So really what we want to talk about is that there are a lot of different strings in Rust. There is, of course, standard string, but there's also the primitive str type, stir type as well. And we're going to be talking about that and trying to figure out kind of what the differences are between the two, how they relate to one another. And so really this stream is aimed at people who have programmed in Rust before, maybe a little bit, have gone through the book. The book mentions kind of what the difference between a string and a string slice or stir is, but we'll kind of try and take an even closer look at that, and write some code to see if we can break things, get some error messages, figure out why the error messages are happening and stuff like that, and then see why we're getting those error messages and try and understand deeply what those error messages are trying to tell us. I thought that a good example that we could do today is kind of reading a file of some sort, a text file of some sort, reading through it, doing some processing on it to try and get familiar with some string APIs that are available to us in Rust. And the text that I have available is actually Faust, which is a German novel from quite a ways ago. It's all in German. Don't worry, it doesn't matter what the text is actually saying. I just thought, why not use that? I believe it's in kind of the common domain and it's free to use, but hopefully this video doesn't get taken down or something like that because I used a 300-year-old play. So we're going to be looking at Faust, we're going to be reading it, we're going to be doing some kind of text processing. My idea was to kind of go through and do something about grouping sentences that feature capitalized words and see, given a capitalized word, what sentences does it appear in and stuff like that. Because that will get us into a little bit of a discussion about what strings are all about. So I think the first thing that we're going to do is just create a project as usual. And so, like always, we'll do cargo new. And I think, this is always the hard part. What are we going to call this thing? I think we'll just call it string proc for string processor. Don't know. Feel free to come up with a different name, whatever you want to use. So we've created that, and I'll go ahead and move our Faust text into this string proc crate that we've created, and go in there, and then I'm going to open it up in VS Code because that's usually what I've been using lately. And here we go. So I think the first thing to do is to go ahead and just run cargo run just to make sure that everything's fine, and we have everything working here. Okay, so I guess the first thing to do that we're gonna to kind of get us started is read the file in. And if you've read the book before, you probably have an idea of what you want to do there. So we can do like let contents equals standard fs read, and then this just takes anything that can be kind of read or can be converted into a reference to a path of some sort, and that happens to be string literals implement that. And of course you could pass in an actual path as well, and there are a whole bunch of things that you could pass in here. If you look here, for those that have not done a lot of API design in Rust before, this is a fairly common pattern where instead of kind of specifying the exact type that you want to take in as an argument, you specify some sort of trait that allows you to convert it, to convert a type, whatever type the caller gives to you, convert it into the type that you need. So instead of taking a path here directly, what the standard library is doing is saying, hey, I'll take any kind of thing that can be turned into a reference to a path, which makes it a whole lot more flexible, so that, for instance, string literals are not paths, but they can be turned into references to paths, which is quite convenient. And so if we read this faust.txt here, of course, reading might fail, so we need to go ahead and I think for now what we'll do is just unwrap. Obviously, if this was a real thing, we might want to handle that error. What happens if we can't read the file? What kind of thing do we want to do? We can change things up, but for us, we'll just crash if we can't read the file because we expect it to be there. And so we have the contents here as a vec. Now, really, probably what we want to do is read it as a string instead, right? We know this is a text file. We don't need to just get it in as raw bytes. This isn't a binary. We can just read it as a text. And so there's a convenient API for that as well, read to string. That does the same thing, except that instead of reading it in as U8s, as bytes, as a byte vector, it reads it in as a string. So basically it calls that read function and then converts the bytes over into a string. And so I guess what we can do now is just go ahead and just a little bit of a check here that we know what we're doing, and we'll go ahead and print the contents out like this. And so if we run it, you'll notice that we've run into an issue here, and this is not good. We have gotten an error here where we have unwrapped on an error, and the error is invalid data that the stream did not contain valid UTF-8. And this is our first kind of important lesson about strings and Rust, is that they are always UTF-8 strings. And so if you're not familiar with encodings and stuff like that, this is a kind of a topic aside it's not really directly related to Rust, but encodings are just a way of actually taking bytes and how do you encode text data into them. And so you've probably heard of ASCII before, UTF-8, UTF-16, Latin 1. There's a whole bunch of them where it just says, given a kind of a stream of bytes of 8-bit numbers, this number 64, I believe, is capital A, and number 3722 is this, and stuff like that. And of course, you can have variable width encodings. You can have encodings that require a fixed width. So there's some 16-bit wide encodings, for instance, on Windows, where every character takes up 16 bits. And so for Rust, Rust uses the fairly ubiquitous UTF-8. Which is a nice encoding because it's backwards compatible to ASCII. So way back in the day, when basically it was usually just English speaking or really Americans working on computers. They didn't imagine that people spoke different languages than them. Go figure. And they just came up with an encoding that worked for the English characters that they needed to use, and of course numbers and some, punctuation, exclamation points, stuff like that. And so if you needed to encode something else, like if you needed to encode, a Chinese character, or Arabic or Hebrew or whatever, then you were out of luck, because this thing could really only just encode English characters, and some, and that, I won't get into the rest of them. They kind of figured out a way to get European languages working with that, because for the most part, they're not too different from the English alphabet, but of course, there are people speak a lot more languages than that, and we need to encode more and more things like emoji and stuff like that. So UTF-8 came about. This is all, long story short, to say that Rust strings require that everything is in UTF-8, unlike in other languages like C, for instance, where encoding is kind of, sort of, sometimes up to you. All that strings in C are just characters, or 8-bit U8s, in an array that is ended with 0, a null byte terminated array. And Rust doesn't work that way. Rust really, all strings have a length, as we'll see in a minute. So they know how long they are, and all the data in there must be UTF-8 encoded. And clearly Faust.txt is not, which is weird, right? It looks fine here and stuff like that. We can read the text there. But I'll just go ahead and do a quick spoiler alert. I changed Faust.txt to be UTF-16 instead. And so the text file is encoded in UTF-16. Rust strings expects UTF-8. And so what are we going to do here to fix this problem? And so what we really need to do is go back to what we were doing before and read in the bytes, the raw bytes that we had. Here, and this is just U8s back and forth that we have, and we need to convert those bytes over to U16s, and then we can there's actually a method on string that allows us to say, hey, construct this string from UTF-16 instead, and it does it. It's optimized basically to do a whole bunch of really fast reading of the byte stream that you're passing in, or really the array that you're passing in, to convert it over to UTF-8 much faster than we would really be able to write today. And so the question then becomes, okay, how do we convert over our vec of U8s to U16s? There's a whole bunch of ways that you could do that. Especially if you're willing to use unsafe, you can basically just say, hey, if I get a slice of U8s, and I know that it's really U16s at the end of the day, I can just transmute them and say, I'll treat that thing as a U16. But of course that requires unsafe. You can do some things where you convert them to pointers and stuff like that. Maybe chat, let me know if you're interested in taking a look at some of that. That's not the focus of today. We're trying to not focus on unsafe today, but if you want to see that, let me know. But really what we can do instead is just kind of go through the vector and convert over our bytes into U16 by hand, in a way that we know is completely safe, or that Rust actually knows is completely safe. Okay, so how do we do that? Well, we want to take our contents, and really what we want to do is get kind of 2 bytes at a time, because our U16s are at the end of the day 2 U8s smashed together, basically. So we'd like to get 2 of them, and if we go over here to the documentation and look at vec, I'm wondering if it has it. Oh, it might not have it. Oh, yes, it does. So really, if I need to do something, I spend a lot of time sometimes kind of just going through the documentation and searching through, and most of the time the names are fairly good. Um, and so it's pretty easy to tell what something is going to do. But I just happen to know that chunks is what we're looking for. And really what chunks does is it returns an iterator over the chunk size. And so we want 2 chunks at a time, and we're going to get an iterator of 2 chunks at a time. You can see here this LOREM lorem. It gives you LO first, then RE, and then M at the end. And so what we can do is call chunks here, pass in the chunk size of 2, and then we want to map over them. And here we're going to get our bytes, let's say, like this. And we know that what we're getting is basically just 2 bytes here. And so what we'll do is just say let first second equals bytes 0 and bytes 1. And so this should give us the first and the second byte. And now, of course, Indianness comes into problem here. We'll have to do a little bit of a check to make sure that we're doing the right thing. To be perfectly honest, I'm not exactly sure what the Indianness of my machine is, so we'll see if this actually ends up working. But if you're not familiar with Indianness, I'm kind of hoping that this goes wrong, so we can talk about it. If it doesn't, maybe we'll talk about it anyway. And so what we want to do here is take our first byte and kind of shift it over and make it the top half of our 16-bit number, and take the second byte and make it the less significant part of it. And so that's fairly straightforward to do. We just first take the first byte, cast it as a U16. So it's now U16, and the top half basically has been padded with zeros, and then shift it up 8 places. And so now we're going to shift that up, meaning, we have 16 bits, the top 8 of which are 0, because we took a 8-bit number and then turned it into 16, which just says, hey, the top half that we didn't have before, just make those zeros. And then we're going to take those 8 bits and we're going to move them up 8 slots in our 16-bit slot and make them the top half of that number. And so then we can AND that together with the second as U16. So now we've shifted up our number, our first number, 8 slots. We take our second number as is, of course, padded with zeros, and then we bitwise AND them together to kind of just say, take that top half and that bottom half and just like stick them together. So now they're one number. And so what we have here is a 16-bit number where the most significant part of it is the first byte in our chunk, and the least significant part of it is the second byte in our chunk. And the more I think about it, the more I think this is wrong, but we'll see. And so we will take that and we'll just call it contents again, because there's no need to take the original. And let's just make sure that we aren't getting any funny business by explicitly saying that this should be a vec of U16s, and it compiles, which is great. So we have that. And so what we can do now is say, okay, let's take the contents and turn it into a string. And so if we go back to the documentation here and go into string here, I think it's from UTF-16, basically takes in our UTF-16 slice here, our U16 slice here, and returns back our string, or gives us an error saying, hey, the thing you gave me isn't UTF-16 at all. And we have a UTF-16 lossy one as well, which basically just goes through and, like, as long as it keeps finding things that it can turn in, like that are valid UTF-16 that it can turn into UTF-8, it will keep going. But as soon as it runs into something that it can't turn into, that is not valid UTF-16 and therefore cannot be turned into UTF-8, it basically just says, well, we'll use this replacement character instead here, because I don't know what you gave me. And this little weird question mark thing, you've probably seen that before, and maybe back in the day more so than now, but when you read a web page or something like that was in the wrong encoding, you end up with a lot of these kind of characters where it's like, I don't know what you're giving me, so I'm just going to show you this this question mark inside of a diamond kind of thing here. But we know that this is UTF-16, and so we're just going to call this one the non-lossy version. So string dot from UTF-16, where we pass in our contents, and then we're just going to unwrap because we're fairly confident that this is fine. Now we're getting an error here because we're passing in a vector of U16s, and it expects a slice of U16s. So instead of like passing in ownership over this collection, it just says, I don't need ownership of it. I just want to be able to look at it. Just give me a view into that collection. And so there's various ways that we can go ahead and get our slice. This is one way that you'll see quite often, where you borrow the thing and then this interesting range syntax here basically says take everything from the beginning to the end. So take the whole thing. If we only wanted up to the 100th byte or something, we could do that as well. But we just want from the beginning to the end here. And so, as long as these unwraps don't, end up getting triggered because we can't read the file, or because, because, I don't know, the thing is not actually divisible by 2, and so we might end up panicking here. That might happen if things are weird, or we can't turn our slice of UTF-16 into a string. This will trigger. Everything should be fine. We should print out the actual value of the file in UTF-8 here. So let's see if it goes, and it did not work. It did not work. So we ended up with an issue. Let's see here. The first thing to do is just to make sure that we're getting the contents that we expect. So let's read here. Interesting. We're getting a whole bunch of zeros. So we've probably, and I figured it out what it is. The thing that I said earlier about and, totally wrong. What I meant was should be a bitwise or. The difference between and or, bitwise and or is basically with and, you're saying if the thing that you're anding, if both things that you're anding together are 1, then you'll get 1, otherwise you'll get 0. And that's not what we want. We actually want wherever the thing is set, we're going to take that thing. So basically, if it's 1 or it's 0, if one of them is 1, then it will be 1 in the, it will be 1 in the kind of output of that. And if both are 0, then they'll be 0. So this basically allows us to say, like, take whatever is in the upper half, take whatever in this bottom half, and then put them together. So we want bitwise or here. And hopefully this works then. Did I not save? I didn't save. Cool. All right, so it's working. We got all of our things ordered together properly. We've turned our UTF-16 file into a string with UTF-8 before. So this is working just fine. And we've kind of overcome our first obstacle here that we've done, where we have successfully taken something that was encoded in UTF-16 and turned it into a Rust string, which we know is always in UTF-8. I'm going to stop real quick and just make sure that there's no questions or anything like that. There was a question about how we know what the original encoding is. The cheap answer to that is I know because I made it UTF-16. So there we go. There are also kind of heuristics that you can tell if something is in UTF-16 or not. So if you open it up, for instance, on my Mac here, if I open up the file in Finder, it will say, hey, this is UTF-16, because it has some kind of heuristic to kind of look through and say, well, it doesn't look like it's ASCII encoded, doesn't look like it's UTF-8 encoded, doesn't look like it's Latin 1. Well, yeah, it looks like if I decode this as UTF-16, I get things that make sense. And so it kind of just figures it out. And a lot of VS Code, I think, also does the same thing. The reason that it's able to read it here is because it kind of like tries in some way to decode it as UTF-8 or as ASCII or whatever. And if it like is like, well, I'm kind of failing here, it eventually gets the UTF-16 and then says, oh, I was able to decode the whole thing without finding any non-UTF-16 code points here. It must be UTF-16. And so that's sort of how that works. Let's see. There was a quick question about if we wanted to change our vec of U8s to a vec of U16s. Now, we can't change vec of U8 to vec of U16 in a very safe way because the layout of vec is not guaranteed to be always the same. Now in practice, we could just basically say this vec of U8s is a vec of U16s and just, it would just work. But that's not guaranteed to always be the case. So from compiler version to compiler version, they might change the layout of vec depending on, if it's a vec of U16s doing something different or something like that. So we don't want to rely on that. But yeah, there was a question of whether alignment would be an issue. I don't think so, because a U16 and U8 should be aligned the same. Anything that is maybe not. That's a good question. But we won't get into alignment today because that's kind of off topic. But we definitely should do a stream on Unsafe Rust where we talk about all these things. And I have done one stream about transmute and stuff like that. So if you're interested in these low-level unsafe fiddly bits, go check that out and let me know what you think. Cool. So I think the next thing to do now that we have a string is to go ahead and go through that string. And the thing that I said we were going to do is basically go through the string, break it up, I guess, by sentences, and we'll have to come up with what makes a sentence, and then find the words that start with a capital letter in those sentences, and then kind of create maybe a hash map where we say, okay, give me all the sentences where let's just look for a capital word here. Project is in, is capitalized in that sentence. So it's kind of like an index into capitalized words. Now, is this useful? I don't know. Not really, but hopefully, it's useful enough to where we can kind of run into interesting issues with it, and you can map it onto project ideas that you might have. Cool. So we're going to create a process function, and the process function is going to take in our string like this, and it's going to return out a hash map. And for now, we're just going to do string to vec of string. So this is the capitalized word as a string, and this here is a vector of all the sentences as strings where that capitalized word appears. So hopefully that makes sense. And one thing that won't work here is hash map is not included by default, so we're going to have to come up here and say use standard collections hash map like this. Cool. So now we're good to go, and we can take that string, and we want to do first, I guess, is break it up by We could try and break it up by sentences, but we don't really know what a sentence actually is. But we can kind of use a heuristic here to figure it out. What we can do first is break up by new lines, because we can be very sure that new lines, if you have a new line, then you have a new sentence. That's what, just arbitrarily we're going to say. And so what we can do is say for line and string dot split here. And there's a whole bunch of split, split. So we have a whole bunch of kind of split type split type methods here that allow us to do interesting things. So we have, for instance, split in, which is an iterator over substrings of a given string, separated by some pattern. And the pattern can be anything. This is another example of where, this is a flexible API that accepts any type P as long as that type P implements this pattern trait. So we have this split in, we have split terminator here, which, an iterator of substrings of a given string separated by characters matched by the pattern. So this is looking pretty good. We might want to do here. Here's an example, for instance, of splitting by periods that might come into use here. And there's also like split white space and stuff like that. So really, it's giving you a whole bunch of ways of how you can split up your strings into different things. And one reason that it's important to get to know a lot of these here is because some can be more efficient than others in terms of, you can get the same thing done, but you might be able to do it in less code or more efficiently if you use the right method on the string. And also, Rust doesn't come with a regex library by default. You have to bring that in from crates.io. And so sometimes it's, it's not a huge deal, of course, to bring in a dependency or something like that. But, it's nice to not reach for a dependency if you don't have to, just because that's going to make compile times a little bit longer and stuff like that. And so if you can just stick to the standard library, which is, in terms of string processing, is okay. It's not the best ever, but you probably want to try and do that before you go off and reach for something a bit more powerful that will ultimately end up increasing compile times a little bit or something like that. But if you need to do it, you need to do it. So I think what we're going to do is split terminator here, which differs from our split terminator, and then it starts from the left. And because we're reading German and English in this text, that are both left to right languages, split terminator goes the right way. So let's do split terminator, and then we can pass in our pattern here, and I think the pattern that we'll pass in is a character. And notice here, this is actually a character because it's in single quotes. If we were to do like this, it would be a string. And I believe, I'm not sure, this would be interesting to figure out if this would match the literal characters, /n, or if it still treats it as the character. I believe it's the literal /n, whereas this will be a new line character, like that. Oh, and in chat, somebody was pointing out the fact that there is also lines as well, which is true, and definitely something that we should be using instead. Why I went with split terminator, I don't know. Let's use lines instead. So we can we'll get our lines like this, and now we have our line. So we have the line that we want. And what we can do now is say we can do split terminator again to get the sentences that we will say sentences are just things separated by periods, which is not exactly correct, but as good as we're going to be able to do for today. So we can say for sentence and line dot split terminator here. So now we have, we're going through, we're getting the line, we're getting each sentence in the line, and what we want to do in that sentence is basically, I think the best thing to do would be to get rid of any white space that's on the end of the lines, and I believe the best thing to do for that is trim. I think here. Yeah, so trim is something on strings where it returns back the string with kind of the white space removed at the end. And so you can see here there's, you know, blank space and a tab at the end with a tab in the middle, and it removes at the beginning and end. So we'll just make sure that we're not dealing with any extra white space that we want here. So sentence.trim here. And that will give us the sentence without any, you know, leading white space, without any trailing white space at the end. And now what we want to do for our capital letters thing is probably split by white space, just to get a list of words that we have inside of that sentence. And so if we say for word and sentence.trim.split white space, and by the way, this is also important, if we go up here, come on, if we go here and look for split white space, it's also important to note that split white space goes off of what Unicode derived core property white underscore space is. And so the Unicode consortium basically comes up with a whole bunch of definitions for what white space actually means, which we will assume that they're going to do right by us here. If we wanted to really make this robust, we would probably look into that a bit more closely. And you also have split ASCII white space, which is really just the ASCII white space characters that you have, like new line and character return and all the fun ones, space, bell, stuff like that. Kind of, you know, if you're doing real serious text processing, then you might want to look into, do I want to split on ASCII white space, or do I want to split on the white space as is defined in the Unicode specification then. And we'll do that for now. So now we're getting the word, and what we want to do is look at the first character in that word and figure out if it's uppercase. And so if you're coming from another language or something like that, you might be tempted to, you know, okay, well, word, and let me get the first thing here, and, you know, it is uppercase or something like that and stuff like that. And this won't work. By the way, what we can do here is we're putting to do down here to kind of make it shut up about the fact that we're not returning our hash map yet. To do here says, hey, I'll get to it. And it kind of makes the compiler play nice. So what we're looking at here, and this is actually a pretty good error message, so let's take a look at it real quick. It says, first it says the trait slice index stir is not implemented for integer. That's not the best error message ever, but this one is better. The type stir cannot be indexed by integer. So we can't, basically what it's saying is we cannot index into our string simply by indexing into it. And the reason, this was a very conscious choice on the part of the developers of Rust to not allow this. And the reason for it is it's probably not what you want. And it even has a a point about this in the book. So if you've read the book before, you might have run into this. And it offers you two alternatives. Which one do you want? Do you want chars.nth or bytes.nth? And that's important to note. Where strings are UTF-8 encoded, UTF-8 encoding is a variable byte encoding, meaning that one character, and there's a very specific kind of definition of character, but we're going to, since we're dealing with English and German here, character kind of directly maps to what you would expect it to map to. Characters can be multiple bytes in UTF-8. So if you have a character coming from, for instance, Chinese, the character set, then you can be upwards of 4 or even 8 bytes long and even longer. So we can't just say take the first byte of the word. I believe in English we could, because English basically is ASCII encoding, and ASCII is really just one byte per character. But for German, I'm not sure. I think for German and UTF-8, it might also always be one byte, but there might be some characters there, like the umlauts, the vowels that have 2 dots above them, or the S set, the big, what kind of looks like a B looking thing, might take up more than that. The whole point is that if we want this to work with more than just English or just German, we need to think about these strings in a different way. And the way that we need to think about them is that they're just a series of characters, but we don't know exactly where one character begins and the other one ends without kind of walking through the entire string. And that's exactly what .chars gives us. .chars here gives us an iterator over a slice of characters, basically. So it gives us a way to look at each character in turn. So we look at the first character and then the second character, and it knows how much to jump forward to get to the next character. So if we're looking at Chinese, for instance, we want to look at character by character. We don't have to look at the character we're currently looking at and say, oh, how big is this in encoding, and then jump ahead that much in the byte slice. Chars will just do that for us. So we'll get each character one by one here. This is a very important point to remember, that you basically, when you're dealing with text and you want to get a character inside of it, the best thing to do is to use chars. And of course, if you want the third character or something like that, you can go ahead and say nth third character, and it will walk it through. But it's important to know that this has to walk through the entire string, because it doesn't know where the third character is. It can't just jump there. It has to go visit the first character, see how big it is. If it's more than 1 byte, it knows, okay, I've got to go that length ahead in the string, and then you get the second character, do the same thing. And so the unfortunate nature of text encoding is that you can't know how far you have to go ahead in the string to know exactly when to get to the other character. That's just the nature of Unicode. And so, there are other encodings where you do have kind of variable byte encoding, and so you can know that, but of course then you end up with text files that are much bigger and stuff like that, because for every character you have to set aside 32 bits or 64 bits or whatever, 16 bits. And so this is the price we pay. So what we want to do is get the first character, right? So nth here, another, and nth means get the nth one, and I believe it is, and it's zero. It's zero indexed, like most things. And so we want to get the first one here, and of course, what nth returns to us is an option, because this could be a string with no characters in it, right? And it doesn't know. Or if we're trying to get the 1000th character and the string is only 3 things long, there's nothing there, and so it will return an option to us. And so we're going to assume for now that all of our sentences are going to be to at least be one character long, which might not actually be true, but for now we'll do that. And of course, return this back to 0. By the way, another way that you'll see nth0 written as is because this is an iterator, you can just call the next function on it, and it just gives you the next one. And of course, the next one is going to be the very first one, the 0th element in that iterator. And so we can say if this character here is uppercase, and you'll notice that, not ASCII uppercase because we don't want to do that, is uppercase here, then we'll do something with it to do here. And you'll notice that there was a whole bunch of things that we could have looked into. So let's look at, and this is on character, is uppercase. And there's a whole bunch of ones. Is white space, is alphanumeric, is control, is numeric, stuff like that. We can even convert them to lowercase and to uppercase. And again, the thing I like about Rust a lot here is that it doesn't really, it is complicated in the fact that, as we'll see, there's multiple types of strings. It cares a lot about the encoding of the string you're looking at, but it doesn't hide these details from you. So even to lowercase, for instance, returns back an iterator of characters, because you can lowercase something and get back multiple characters. There are some characters that their lowercase version is itself multiple characters. And most languages that I've used before, to lowercase just returns one thing always, because it just assumes that lowercasing something always returns a single character, which is just not true. There are languages where that's just not true. And so you're going to pay a little bit of a price in terms of complexity. And Chat was just mentioning there's no more complicated than any other language that treats strings properly. I think that's absolutely true. Strings are extremely complicated, and so the fact is that it's not Rust here necessarily that's making our lives complicated. It's strings. Strings are just complicated. Human language is complicated. You can pretend that everybody speaks English and go on with your way. If you want to do that, that's not a very nice thing to do. And so if you want to, give people proper respect and use their language, you're going to have to deal with the complexity that comes with that language. Okay. So we've gotten the next character, we've unwrapped it because we're sure that it's going to be there, and we'll see if that explodes, and we've checked that it's uppercase. So now what do? We know that our word's first character is uppercase, and so what we probably wanted to do up here is get our result as a hash map, and new, like this, and so we've got a hash map here, and we said that this hash map was going to contain the word as the key and a vector of sentences as the value. And so that should be pretty easy to do. We just take our result and we insert the word that we got, right? And okay, what do we do here? We could, of course, do vec here, where we create a vector, and then we stick in the sentence like this, and that's all well and good, and then we can get rid of this to do down here as well, which is great. Oh, actually, let's not get rid of it just yet. Of course, this is not really correct, right? Because if word already existed in the hash map, then we're just going to overwrite it with the previous sentence. So really what we want to do is say, give us the entry inside of this hash map if it exists, and otherwise give us kind of the default or whatever. And luckily, Rust comes with a pretty nice API for doing this called entry. where we just say entry here, and entry gives us an entry into that hash map. Whether it exists or not, it gives us a kind of a logical thing for saying this is an entry into your hash map. And then we can say, give us if it exists, give us that thing, or give us a default. So this will give us a vector if it exists at that key, or it will give us the default vector that we wanted right here. And then all we have to do is push our string onto that right here. Let's see what's complaining about here. And here, or default is we run into the fact that we don't know. Up here we just said hash map new, and it doesn't know what type hash map should be. And so we'll go and we'll say hash map string, just like a return type, right? String here. And then we can return our result here. Not return. And we should be done, right? This should be it. But we're running into a problem that the chat has already, I see, has pointed out here, where our types are not quite lining up. So the error message that we're getting is that we expected our key here to be a string, capital uppercase S string, but what we found is this ampersand stir instead. And so we're not passing in the right type. And so the first thing that I see a lot of people do when they get into Rust is the easy thing, and they say, well, this is the wrong type. We expected this to be a string, and I got this weird ampersand stir thing. How do I turn an ampersand stir into a string? And they come over to the docs, and they go over here, and they say, okay, stir, what's that all about? And come here, and say, okay, this is the module. Let's look at the primitive type, okay. And they're looking, and then eventually they're going to find something like toString here. And like, great, this takes a ampersand stir, which is what self is here, and it gives me a string. That's exactly what I need. So toString here, and that's great. And then, it turns out that this string here is also causing me issues that I have. Oh, and it's not string, it's a sentence. So this is also causing me the same issue. So I just go over here and I do toString again, and shut up stupid compiler, and we're great. Oh, happy day. Which for some applications is going to be totally fine. Like, but we shouldn't just do this blindly. We should understand why the compiler was complaining and why toString is probably not what we want, and so that we can make the smart decision of whether what we're doing here of converting these into strings is the right thing to do at all. So that's what we're going to discover next. Any questions so far? Getting myself a little bit of water. Sorry if that caused a lot of noise. Apologies. All right, cool. So we're going to take a look at this here and figure out what's going on. So it's important to it often gets asked, why does Rust have two string types, this capital S string and this ampersand stir string, and the answer I like to give is, well, it doesn't have two string types, it actually has like 7, so it's more complicated than that. But as far as why there is this capital string and a lowercase ampersand stir is that they represent two different things, and so we're going to look at what they represent first by coming up here and just repurposing our program real quick to kind of inspect what is going on. And so what a capital S string is an owned string. You have ownership over it, meaning if you have, not an ampersand string, but the string itself, when it goes out of scope, when you have ownership of it, it will be destroyed. It will be dropped, and that means that the value of that string that's probably living on the heap somewhere will be cleaned up, and that memory will be returned back. What an ampersand stir is a string slice or a string view. It's really a way of looking at string data from some point in memory to some other point in memory and saying these bytes that I'm looking at here, they're string data, they're UTF-8 encoded data, and I don't own it. And you'll notice that what we're dealing with here are a bunch of ampersand stirs, right? This is a reference at the end. This stir is a string view, but we're taking a reference to it, so it's really pointing up to this string data that exists somewhere. And in fact, there's already there's kind of a dual to string and stir that exists in the standard library as well. And you can really think of them basically in the same way. And that is, you have vector and slice of whatever that vector contains. So it's vector of t and slice of t. And string and ampersand stir. So just as vector is an owned collection of type t, and this slice here is a non-owned view into some collection where everything in it is type t. Same here, string is an owned string where when it goes out of scope, it's going to be destroyed and that memory is going to be cleaned up. And ampersand stir is just a view into that data. And so it doesn't matter, when we stop looking at it, somebody else owns that data. Or in fact, you may have seen something like this before, ampersand tick static, and that means that nobody owns that data. That data is really like baked into the binary inside of our data section, and we're just looking at it. Nobody, we're not taking ownership over it. We're just kind of viewing it. And these are really kind of parallels with one another. And so a lot of times you'll find that the ways that you kind of talk about and go between a vector and this slice is the same way that you talk about and go between strings and string data. And to go one step further, strings at the end of the day actually are vectors of bytes where those bytes are UTF-8 encoded, and that's basically all they are. And so I don't know if this is officially kind of, I don't believe that this is 100% officially baked into the language, so you can't 100% rely on it. But as of right now, strings really, I believe, are kind of really modeled as vectors of bytes, where the data is just checked to be UTF-8 compliant bytes before, as we construct it. And so really these things are kind of the same thing at the end of the day. And I thought one way to kind of really, an interesting way to look at that is if we have a string here where we say string from hello, like this. One interesting thing that you can do with strings, if we go all the way back up, come on. If we go into string, you'll notice some interesting things about it. For instance, you can call as pointer here to get a pointer to that data. You can call dot capacity here to get the capacity, and we'll talk about what capacity is in just a second. And you can call .len here to get its length. And length, of course, is the number of bytes that string has inside of it. And remember, this is important. It's the number of bytes, not the number of characters or graphemes in the string. So if you want to know how long the string is, you can't just say .len to know that's how long it is in bytes, but how long is it logically in characters? You have to call .characters, .count or .size or whatever to get it to get the size of the character iterator. So the reason I bring that up is because at the end of the day, that's actually what a string is. A string is a pointer to the data on the heap, its length, and its capacity. And capacity is simply how much room has been allocated on the heap so far for this string. I might not be using all of it. I might have a string that's taking up 10 bytes, but I might have allocated 16 bytes for that string to exist. And so if I add something, if I add let's say 1 byte to my string, I know I won't have to allocate for that because I have the capacity to go. And once I go past that 16 byte capacity, how do I get more capacity? I allocate. And I will actually get more space on the heap from it, and the capacity will go up. Great. So let's take a look at that real quick, and really in concrete terms. So we're going to print out here, if we can do this, print out string dot as pointer, and not as could do mute pointer, but we'll just do as pointer. The same thing at the end of the day. Then we're going to print out the length of the string, which should be in bytes because these are all ASCII characters here, 1, 2, 3, 4, 5. So hopefully this is 5 here. String dot len. And then we're going to print out its capacity. And we're not really sure how much capacity is here. It's kind of an implementation detail to know when we're converting from a string literal, how much capacity will be created on the heap. I imagine it's whatever the length of the string is, but we'll see. And so string dot capacity here. So this is great. We've got the pointer, we've got the length, and we've got the capacity, and we're just going to print them out. So let's go ahead and do that and run it here. And you can see our string is living at this address somewhere in memory. It's got a length of 5, and it turns out the capacity is 5. So there's 5 bytes, reserved for this string on the heap. And if we push a character onto this string, we're going to actually have to allocate again. We can be sure about that because our length and our capacity are the same. There's no more room on the heap for data here. So if we need more room, we're going to have to allocate for it. All right. Another way to really drive this home about this that I find interesting as well is to look at what the string is as bytes. And so there's a way to do that where we say, I'm going to transmute from a string to where it will just be an array of bytes that is the same length as however big a string is. And we gotta close this here. And we got to call it on string like this. And it looks like I screwed the pooch here. And it's because I'm forgetting the turbofish operator here. Oh, and it's saying that this is unsafe because it's very unsafe. So again, what this is doing is it's saying this, I'm going to pass you a string, and I want you to just pretend that it's an array of U8s that is as long as however a string is in memory, whatever the size is of a string. And by the way, this is size of string, so we should make sure that we understand that string is a struct. And when we're getting the size of the string, we are getting the size of that struct in memory. And what we're going to see is that strings are really just a pointer, a length, and a capacity. That's all they are. That's the only thing that's sitting on the stack. And the actual string data is somewhere on the heap, somewhere else. So let's go ahead and run this. And you'll see down here that we have our, again, the address, the length, and the capacity. And you'll see here, and you have to turn it around because it turns out this is a little Indian machine. That if you read it from right to left, this is the address that we saw, 7F, B6, blah, 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 all the way here. Padded out or here's 5, some padding zeros. 5 is the length or the capacity, I'm not sure which one, and by the way, it's not set. It could be the length or capacity depending on which version of the compiler we're on. It's an implementation detail. So we'd have to do a little bit more experimentation to see in this version of the compiler, where does it place the length and the capacity? Does it place capacity second or the length second? We can't know because they're the same. And here's capacity or length, whichever this was not. So really, this is what a string is at the end of the day. It's a pointer, it's a length, and it's a capacity that sits on the stack. And when we actually go read that data, we have to go to the heap to read it. Now, if we do the same thing, and we'll just move this out here, let str and pass an str here, and we're going to do the same thing here, where we're just going to get the memory. We're going to take like a real close look at the memory of this string slice here, and just really take a good look at it and see what it's all about. So let's go ahead and run this. And you'll see that it's a little bit different. What we have here instead is an address and a length. So if you want to know what the difference at the end of the day between a string, capital S string, and an ampersand stir is a ampersand stir is a pointer, a length, and a capacity. And an ampersand stir is a pointer and a length. And the reason that this is different is because ampersand stir, you can't mutate it. You're really just looking at some string that somebody else owns. You don't own it, you're just looking at it. And so how much capacity it has is not really relevant because you're not even potentially looking at the whole string. You might be looking, you might be looking at a piece of it. You might be looking at only one part of it. And so really the capacity is of no bother to you. It's really where does this string data start in memory, and how many bytes long can I look at it before it's not the string that I'm worried about anymore, it's some other. And chat pointed out as well that the name for this is a fat pointer. So it's just a pointer plus a length, and you will see that in other places in Rust. Again, we learned earlier that ampersand stir and a slice are really kind of one and the same in a way, and that's because they're both fat pointers. They both are a pointer, so some memory address, and the length of how long that they go for. So hopefully that wasn't too much of a deep dive there. That is kind of in real concrete terms, memory-wise, what the difference between the two is. But let's examine our code again and see a little bit, kind of a little bit more of get an understanding of why we are looking at ampersand stirs here, which we can see we're getting versus getting strings. And the reason for that is we're passing in a string here. This is owned data. That means at the end of process, here, string will be dropped, and the memory that string refers to on the heap will be cleaned up. That string will go away. When we call string.lines here, the issue that we have is that we are going to be looking into that string data. We're going to be looking at the heap where the string data lives, and we're going to be just getting kind of little views into each line. So we don't want to get, an own string. We don't want to drop, when we stop looking at a line, we don't want it to drop and then clean up that memory. That would be a problem because that's going to happen at the end of process here. We simply just want to look into that string and get like a little view into it, a little window into the string. And so that's why all of these here are returning ampersand stirs here. They're returning this little view into the string that gets passed into process here. Does that make sense to everybody? And so when we get here, what we have here is an ampersand stir, but what our hash map is expecting is an own string. It's saying I want strings that I own, that I've got, I am in charge of when this thing will be destroyed, when I am in charge of when I will clean up the memory for this thing. And so these are two different things. And of course, one way to turn our ampersand stir into a string is to call this toString function on it, which basically what it does is it just takes that ampersand stir, it takes the view into it, looks at it, and just copies that memory. Says, okay, I'll take a copy of that, I'll just take every byte, copy them, and I'll put it on the heap somewhere else, and I will create a string struct, with a pointer to that new memory that's been allocated newly on the heap, and the length and that capacity. I will do that. I will copy that data. So we're essentially, every single time that we call .entry here, word to string, we are allocating new string data. So we're ending up with, however many words, however many times we reach this code here, we're allocating a new string for word and a new string for sentence. And that's a little bit unfortunate, right? It would be much better if we could just say, let's return this hash map where instead of getting new strings where we are the owner of, we're going to return back views into the string that we've passed in. And so really what we want to do here is something like this, give me a view into, back here, give me a view into the original string where the word is capitalized, and give me a vector of views where we're looking at those sentences where they are instead. But as far as who owns that string and who's going to be destroyed, it's somebody else. We're just looking at the data that is owned by somebody else. And so, by the way, real quick before we get rid of these two strings, another way to write this, and one that I usually prefer, is toOwned instead of toString. And what that does is say you have some data that is the borrowed version of something, take that borrowed version and turn it into the owned version. And so we're taking a ampersand stir, which is just borrowing data, it's just looking at data, and saying take that and create a copy of it that is the owned version of that. And so what this goes from is a ampersand stir to a string instead. But of course we don't want that anymore. We just want to look at the string view, and get rid of this. And we don't want string anymore. We just want to take the view here. And of course now what it's complaining about is that we're returning back a hash map of ampersand stir and a vec of ampersand stirs, but up here in the return type we said that that's not what we were going to do. So let's go ahead and change that. All right, so we're almost working here, but we're running into an issue here that, well, simply, I guess the easiest way to think about it is we are missing some syntax. We're simply just, it's saying we're missing a lifetime specifier. So this is one case where we need to put in lifetime specifiers. And so maybe the first thing we can do is just kind of, I don't know, why are we doing this? Why are we putting tick A here and putting it here? Just because the compiler told us we're missing that syntax, so we're going to put the syntax in. So that worked except for down here. If you've been thinking about ownership lately, you've been getting a better idea of what ownership is, try and think why this is an issue. And maybe you've watched John's video from last week, or my video from last week, and thinking about ownership. When do things get destroyed? Are we returning back references to things that are destroyed? And hopefully this is clear to you why this does not work. These ampersand stirs here are basically logically views into the string data that we're passing in here. We're returning those views from this function. So we're returning views into a string that we're passing into this function, but we're passing ownership. So at the end of this function, string will be dropped. And when string is dropped, that data is no longer valid. So what we end up with here is views into a string that has been dropped at the end of the function. And we have dangling pointers here. This is not correct. Rust is preventing us from having dangling pointers. And so what we need to do is, there's two ways to solve this. One is do what we did before, where we copy that data and say, it doesn't matter, you can drop the original string because we're just creating new copies of it on the heap somewhere else. And we're in charge of when those strings get dropped, so don't worry about it. That worked. That's why the code before compiled. But we decided to switch to using these ampersand stirs here because this is more efficient. We're not allocating new things on the heap every time. So how can we change it here? Well, what we want to say is let's borrow this string here, and however long that we want to make sure that this string data here lives for however long that the string that we're passing in lives for. So we do it like that. And I have no idea why it's saying down here that the function process is never used. That's kind of weird. Anyway. So this works. This works now because what we're saying is that the string, we're borrowing the string here for some lifetime A, for some period of time A, and the views that we're getting back in this hash map live for at least that long. They might not stick around for quite as long, but they at least live as long as this thing. This thing, or a better way to say it is, this string will stick around for at least as long as these slices stick around. And so we don't have to worry about string being dropped, but while these things are still viewable, still usable, because that would be a dangling pointer. Okay, I'm gonna shut up now. I think that was hopefully a somewhat clear look into strings. One other thing that we can do here, we can, instead of taking an ampersand string, so this is just taking a reference to that struct. We saw that struct where it was a pointer, a length, and a capacity. We're borrowing that. We're just pointing back to that original struct that's sitting here up on the heap. That's fine. This works after all. What we can do instead is say, take an ampersand stir here, and this is saying, don't give me a reference to that, that own string struct. Just give me a view into some string data. And this works just as fine because when we pass in, we can call process here. Of course, if we call process with our string here, it doesn't work because it's expecting, we're passing in an own string. We're trying to pass ownership in the process. That's not what we want. But if we call like this, and it's called contents, sorry. If we pass it like this, then sure, what we're actually passing in is a reference to that string struct that we had, but if I can find it in the docs, bref, and string implements deref where the target is stir. And so when you dereference a string, you can get a stir back instead. So just to read what deref does here. And actually it's not deref that we're looking for. I think it's asref, right? Yeah. This is what we're looking for. So deref is the opposite of asref. Where is... here. What asref says is, given this one thing, I can get a reference to this other thing. And so there's an implementation where it knows if you give me a reference to a own string, I know how to get a reference to a stir. So this is a little bit of magic that the Rust compiler does, where it will automatically do this referencing for you, where if you pass in a thing that knows how to be referenced as another type, it will automatically do that for you. And so this works out where our ampersand string automatically gets turned into an ampersand stir, which is a totally fine thing to do. It costs nothing. They're really logically equivalent. This ampersand stir here just refers to all the contents of the string that we've passed in. Maybe another, there are other ways to write this, but this is kind of the most common. Okay, so I'm going to stop for some questions real quick. We've got about we've got a few minutes left, and I'm going to talk about some other types of strings in Rust, and why you might want to use them and stuff like that. But I want to take any questions that you might have around ownership of strings, difference between ampersand stir and string, and stuff like that. So do you think it's unfortunate that string, which seems to be the default string in Rust for newcomers, actually is a harder object to manage? I'm not sure what you mean by it being harder to manage. And I'm not sure if it is the default string, just because string literals, right? What is the type of, if we do let path equals faust.txt, and you can even see it already here, this is an ampersand stir. So string literals are ampersand stirs, right? Because they're just views into this text data that is literally going to be baked into our binary. Our binary, if we were to run, I think we cargo build, not built. This actually might be, but it's still there. So if we, do I have strings? Yeah, I think this should work. If we call strings on target release, target debug here, and then pipe that into less here, we should be able to see that's not the exact one. Strings is not working as I would expect it to, but in any case, faust.txt here is really baked into our binary. So this ampersand stir here is looking into the data inside of our binary. So I'm not sure if I would say that it's the default per se. Could strings in Rust be easier? Perhaps, although I'm not exactly sure how you would do it in an easier way so let me say this. They could be easier. Could they be easier and as correct as they are? I'm not so sure. That's hard. Strings are complicated, as we already said. So with Serde, we can do both ways. I mostly see string versus stir. With some effort, both can be supported, but I think I've never actually seen that in practice. So Serde, so let's pretend you have some struct, my struct here, and you're going to call derive deserialize, which if you're familiar with Serde, this is a proc macro in Serde that allows you to derive how to deserialize types, and you do data string like this, and let's say deserialize. We're gonna have some function deserialized here, and we call Serde JSON from dir, whatever it is, where we pass in, let's see, I don't want to write out the whole JSON struct, but just pretend this is a JSON struct that represents this my struct thing where it has a data thing that's a string, and you say, you know, s is my struct, like this. What Serde will do here, because this is an own string and we've explicitly specified it as an own string, what Serde JSON will do is we'll take the string, the data string here, we'll look inside of the string here, and you know what, let me go ahead and write it. Data hello world. It will look inside of the string and it will find the string slice, the ampersand stir hello world here. It has a view into this string, and we'll take that, and it will, you know, I don't know exactly the implementation, but it will most likely call, you know, to owned or whatever. It will copy that data into the heap and create an owned string now. So there will effectively be two versions of this hello world data, the one that's coming from this, you know, this string here, and the copied version that's coming that now lives inside of this struct. And so their lifetimes are independent. This string, you know, if, let's say this wasn't a hard-coded string literal, but coming from the network or something like that, you know, it doesn't matter when this thing gets dropped, when it goes out of scope, when it gets destroyed, because this is now a copy. We've asked, we want ownership over this string. And the only way to have ownership over this string that you're only viewing the string here is to copy the data. So that's what we're doing. We're copying the data. Now, we could instead do something like this, and of course we'd have to specify a lifetime and stuff like that and here. And basically what this will tell Serde is, I don't want an owned version. I want a view into string data that relates to this data here. So really, I just want to look at this thing. And of course, when we actually would call this, we'd have to probably do a little bit more plumbing to make sure that Serde understands the string here is a view into the string here. So their lifetimes are related to each other. But what this is saying now is, I don't want ownership of it. I just want to look at it. So now my struct's lifetime is tied to the lifetime of the string that was passed to from stir here. And so if this string, you know, again, if this was coming from the network, we deserialized it, and, you know, at the end of deserialize, we dropped the function. We can't return my struct out from deserialize because that data has been cleaned up. It's been dropped. It's been cleaned up. It no longer exists on the heap. And so this effectively ties the two together. Now, why you might see string like this more often than ampersand stir is because this, you pay the runtime cost of copying the string data, but it's ultimately more flexible because you no longer are tying your struct's data to the original input data. They're no longer tied to each other. You own this string. It's your own copy. You can do whatever you want. You can make this thing live for however long you want to. You don't have to worry about the input data anymore. And that's just more, it's easier, it's more flexible. And so you'll often see that because, you know, hey, copying data, you know, if you're doing a simple app or something like that, maybe it's not that expensive at the end of the day. Cool. Hopefully that answered your question. So would you consider the process function as idiomatic Rust? Because of the nested for loops here? I don't know if I would, I'll say this, I don't know if I consider this not idiomatic Rust. Is it the best way that you could write it? Probably not. And certainly here, you know, you might want to return a result instead of a plain hash map because we're doing some owner apps here and stuff like that. But yeah, could you use some things, some closures, and use some iterator functions and stuff like that instead of just doing for loops? Yeah, absolutely. For these nested type things, in this particular case, I don't know why. I just started writing for loops. It seemed nice to me. For loops, I would not consider for loops to be unidiomatic Rust. Rust is definitely a language where it feels at home to write fancy functional style iterators, and it feels at home to write for loops, as long as those for loops are not, indexing into things. Both kind of have their place. And if you're curious which one is better, it's which one do you find easier to write and more readable. And most of the time, as long as you're not indexing, this probably is as efficient as any iterator would be. So hopefully that answers your question. So back to the default question. Default in the sense of notation, string seems more important than ampersand stir. Yeah, I don't know. That's a good question. Yeah, I'm not sure. So there was also a note in chat, string is a wrapper over vector of chars. So just to be slightly pedantic, that's not actually true. And the reason to be pedantic is because this is a little bit of a point of confusion if you're coming from C. In C, the char type is 8 bits wide. It is effectively a U8. So, and in Rust, the char type, let's go take a look at it real quick, is not 8 bits wide. Because a char represents a single character as in a Unicode scalar value, and that means that it has to account for all of Unicode, which can be quite large. And so, as far as I'm aware, char is 4 bytes wide. So a string is really a wrapper around a vector of U8s, a vector of bytes, not a vector of chars. So just a little bit of pedantry for you. Let's see. So could string literals be from ampersand stir instead of ampersand stir? I'm not sure what you mean there. They are ampersand stir just because string literals are always going to be baked into your binary. So you're taking a view into data, basically, that's inside of your binary. But maybe you could clarify what you mean. Cool. So we're reaching the end here. I really hope this has been quite different than the last stream. I still hope that it was helpful to you. I want to go over a couple of other string types. I made the slight joke earlier that people ask why are there 2 string types in Rust, and I usually answer with there's not. There's more like 7. And that's because there are quite a lot of them. So we have our normal own string. We've talked about that. It's UTF-8 encoded. We have ampersand stir, which is a string view, a view into UTF-8 data. So that's great. Then we also have C string. Now C string is usually is basically exactly equivalent to I shouldn't say it's exactly equivalent to an actual string in C, but it is meant to stand in for it because it's used for FFI with C. So it is going to be a string of bytes that has no 0 in it, and at the end a 0 is there, which is basically what string data is. And as far as encoding goes, there's not a lot there in terms of what encoding C strings use. It's kind of up to the caller there, what they're expecting. So there's not a lot of guarantee there. It's really just kind of a fancy 0 terminated vec of U8s at the end of the day. And you can turn it into, you can get a stir from it. Of course, if it's not UTF-8, you'll get an error. You can get a stir lossy where it will try as best it can to turn it into UTF-8, but if it can't turn a particular thing into UTF-8, it gives you that replacement character that we talked about earlier. So very similar to that. You can, same thing, you can get strings from it as well, as long as, you know, it will try to turn it into UTF, or treat it as UTF-8 if it can. When do you want to use C string over string? Only if you're doing FFI. So if you need to talk with C, and you want, and a C function expects a C string, then you can use C string to help out with that. So you have some functions to help you with that. So C string is almost never used unless it's with FFI, which is why it's in the FFI crate that you have here. You also have C stir here. C stir is basically the equivalent of ampersand stir, except that it is just like C string, SC string view, basically. So really same kind of difference between the two. And when do you need this versus an own C string? Well, when it's really about ownership, and do you have ownership over the data? Are you in charge of dropping it, or are you simply looking at that data? And if you're simply looking at it, then you want C stir, and if you're in charge of dropping it eventually, then you want C string. And you can see a whole bunch of things about creating one from a pointer, getting the bytes with null unchecked as pointer, blah blah blah, 2 bytes, the whole thing. So that's really easy. There we have then OS string. OS string is a string that is dependent on what operating system that you're on. So it has a layout here of on Unix systems, strings are often arbitrary sequences of non-zero bytes. So they're normally C strings, which can be interpreted as UTF-8 sometimes. And if you're on Linux or something like that, you may have run into an issue where you have a file system that it is not encoding in UTF-8, and then you might run into some issues there. So like OS string is not necessarily UTF-8, even on Unix systems, but like maybe it is. So you don't know. On Windows, OS strings are similar to the file that I showed at the beginning of this. They're 16-bit values, so they're wide character strings. And they're interpreted as UTF. They can be interpreted as UTF-16, and so each character is 2 bytes, or kind of each sequence of value inside of it is 16 bits wide. And so when is this interesting to use? I think, for instance, if we look in the env. If we look at args here, no, not args. Well, what does it? I think if we get, there we go. Interesting. Yeah. So we have var and var os. This fetches an environment variable, where it returns you back a string. Of course, the environment variable's value must be UTF-8 encoded then. If it's not, you'll get an error. But if you want to not worry about that, then you can get an OS string. So this returns you back an option. It's either there or not, but you'll always get an OS string because by definition, it is a string that is valid for that platform, whatever platform you're on. So when do you need to use OS string? And by the way, this is OS string and OS stir, same difference as before, where OS string is owned, OS stir is just a view into an OS string. So kind of same difference here. When do you need to use this? Well, when you're dealing with the operating system, for instance, you'll oftentimes get OS strings back, or you'll have to deal with values like, for instance, var here, where if it's not UTF-8 encoded, you'll get an error. And so you have to decide, do I expect that as ever a possibility? If I do, then if I do expect my values to maybe not be UTF-8 encoded, then perhaps I want to use the one var OS, which returns back the OS string instead of a regular string, right? So that's that. What else do we have? We have some extensions on path. I should mention path because path is effectively like a string, or rather a str. You have path and path buff. Path buff is like string. Path is like str. Same kind of distinction as well. And these are really just wrappers around OS strings that give you path specific things. And you can see you can turn it into an OS str without there's not a result here because this will always work because at the end of the day a path is really just a wrapper around an OS str. And that's why I've often seen code that deals with paths where they constantly trying to turn those paths into strings, and you always have to deal with the possibility that those strings the paths might not be UTF-8 encoded, which is a possibility. And so they're unwrapping things, and we're just kind of hoping and praying that that the path that your program deals with is UTF-8 encoded, because if it's not, the whole thing's going to crash. It's better to probably just keep things as paths as long as you can, and there's really not normally a need to turn it into to a string. If anything, you can turn it into an OS string if you absolutely must. So that was kind of a look at strings. It's not everything because we didn't touch on FI and stuff like that, but we did a bunch. We looked at a bunch of high-level APIs on strings. We talked about the difference between string and ampersand str. We talked about the different types of strings that you might might deal with, whether that's the regular string and ampersand str, whether that's C string and C str, whether that's OS string and OS str. Paths are another type of string as well. So I hope that there was some things that people learned today. I hope that this was useful. Let me know if it was useful, and if in particular how you like this style where it was there was code but maybe not exactly as much code as there was before. I'd love to hear that as well. I think we'll end it for today with some questions, if there's any questions left. Would a str be useful on its own, or does it only make sense to have a str? So the question is whether it's useful to have a type where it's like foo is a str, and we can do this too. And the answer is that you can't have just a str. The reason is strs do not have a size known at compile time. So just like unsized arrays like this, oops, sorry, wrong place to put it. You can't also have this for the same reason, because what we're doing here is we're putting a variable called foo on the stack, and what Rust needs to do right here is say how much area on the stack does this occupy. And for a vec of U8s, well, how much room does it take up? Well, it's a pointer, it's a length, and it's a capacity. So that's, what is that? Probably depending on the size of your system, like 8 bytes for the pointer, and then 8 bytes for the size and 8 bytes for the capacity. So 24 bytes. That's easy to know. But how big is an unsized array of U8s? It's an infinite size, any size, we don't know. We don't know how big this is. Just like how big is a string view, we don't know. We only know when it's behind this indirection, when it's behind a pointer, when it's behind a fat pointer that tells us how long the length is. Then we know how big this is, and how big is this? This is a pointer basically at the end of the day. So on my machine, it's 8 bytes big. And so does it ever make sense to have a str without an ampersand str? not in kind of not in reality. Like there are places where you might need to name just a stir because a pointer to it or a reference to it is kind of assumed in the code, but you'll never write code like this. That just doesn't make sense. I hope that answered it. Box stir is a good example of that because again you're behind indirection again. So now we've put this view on the heap, and we our box now can keep track of the length, and so this is possible because how big is this? How much room on the stack do we need to actually set aside for foo here? However big a box is, and if, I believe a box with the unsized type is two pointers or two U sizes basically. All right, any other questions or anything like that? Just a real quick last thing for everybody. If you want to know when, if you want to know when I am going to stream next, the best thing to do is to follow me on Twitter. That's where I announce it. So, and please let me know about your feedback. That would be super awesome. I'm trying to it's a holiday today in Germany. I still stream today because I wanted to get in the habit of doing it every Friday. So we'll see if that works out, but please let me know if you liked it and what I can do in the future. Next week will probably be, either some FFI stuff, or if I'm feeling crazy, maybe some async await. We'll see. So just let me know what you think about that. And I appreciate everybody for watching today, and have a good weekend, everybody. Thank you very much.